last time we started, I guess the theme of the week, so to speak, is like getting into kind of more practical, messy details that you encounter in real life. Like most of the stuff we did was like kind of background stuff on optimization and control and like basic algorithms, right? How to do trajectory optimization, how to do MPC, convex, non-convex, blah, blah, blah. And now we're kind of starting to get into these issues that you will see if you start to put this stuff on hardware and get out of simulation, right? So last time we did this iterative learning control stuff. And this is part of, like a very broad scope of like things you can do when there is, the current popular term for this is sim to real gap, but, model error, model mismatch, where the real system doesn't exactly match the predictions from your model or your simulator, right? And so you have some error in what you offline optimized or designed, your feedback policy. When you put it on the hardware, there's some issues. So the question then is, how do I deal with those issues in a data-driven way using data I get from the real hardware, right? So one way of doing it is this iterative learning control thing. It has pros and cons. Like the pro is it slots very nicely into the set of tools that we've been talking about, and it's extremely data efficient. The con is that its like scope is pretty narrow, right? It's basically just for adapting your open loop controls if you have a given trajectory. So the context in which this was invented is like industrial robotics, where you're doing a repetitive task. If you're just trying to do the same repetitive task over and over again, this works amazingly well. But if you need to generalize away from that somehow, maybe not the best idea. And we kind of talked last time about sort of broad range of ideas and techniques in this general area, some of which involve trying to improve your model or just improve the control policy, right? And this whole thing fits into the broader scope of adaptive control or online learning, kind of these kind of things where you're trying to use the data on the hardware. Maybe you did some stuff offline and now you're trying to fix up the kind of iron out the little wrinkles, maybe the things that weren't exactly the same, right, on the hardware. So questions about that? Yeah. Mm. Oh yeah, totally. Yeah. So like variations between hardware, on the same, nominally the same robot. If you have little, little things that are off, this is like 100%. Yeah. So like where this stuff comes from is actually 80s, maybe even back to the 70s, like industrial arms in factories that are constantly doing the same assembly task, where over time you have wear in the components, like, bearing friction changes over time. So you would just basically run this constantly while the thing's doing the same task every time, and like all these little errors, you can just mop them up with this super cleanly, and you're kind of just always doing this online. So it's perfect for repetitive tasks, like classic industrial robot stuff is where this comes from. But also in more recent times, people have deployed this on drones and all kinds of insane things. And yeah, you can do some really impressive things with it. And it scales to really complicated, really big systems really nicely without needing a lot of data, which is the cool part. And generally, I just think you guys should know about it because it seems to have been somewhat forgotten in the last decade, and it's super effective. It's basically super complementary to a lot of the RLA. Like it works really well in settings where you can't get a lot of data. Anyway, okay, so that's that. Any other thoughts on this? All right, cool. So that was last time, and today we're going to start getting into um, a different kind of like end of this messy real life sort of story. We're going to start talking about stochastic optimal control. And we'll see how far we get with this. There's like a lot to talk about. And so the idea here is, even in the ILC context, there we had model errors, say, where there were just things that were wrong about our model. But in everything we did last time, we still assumed that we had full, clean, essentially perfect measurements of the whole state of the system, right? We're assuming with direct access to the states, and we're plugging those back in, right? So it was still deterministic. There was no noise, and we had full state observations, right? So now what we're going to talk about is, which is an orthogonal kind of problem, right? Is situations where you do not have direct access to the states, and maybe things are noisy, of sensor measurement kind of errors, that kind of stuff, and what that does to you. Questions about that? Cool. All right, let's do it. So I guess I should write that down. So far, we've assumed we know the system state. And the big question here is what happens when all we have are noisy measurements of not even the state, but quantities related to the state. And that's the real situation. Like there's a sense in which states are not real. States are like totally made up. And like in some sense, they're just the things that you need in your model or your simulation to like make it work, right? Um, the only thing that's real is the things you send to your actuators and the things you measure from the sensors, right? Like the state thing that like kind of lives in the middle there is this fiction that we make up because it's convenient for ourselves. Um, and you can never really measure it, right? So let's see what happens when all we have are noisy measurements. One of these related to the state. And so, I mean, this is really always the case, even in context in which you have like pretty good measurements, like say if you're in a motion capture arena. There, I mean, those things are pretty good. You can get like sub-centimeter accuracy measurements on these markers, right? And they'll give you the full rigid body pose. But even in that context, those things will just give you the pose. They won't give you the velocities. And there's always kind of like, and you can figure that out a bunch of ways. But even there, it's a little subtle, right? So those things do have error. And if you were to naively say finite difference, the stuff coming out of that thing to get the velocity, well, finite differencing introduces noise amplification and all kinds of potential badness. So even there, it's not a great idea. The other big gotcha with mocap systems, they have delay. If you're doing something like flying a drone around, if you try to, has anyone ever tried to close a feedback loop on a drone in a mocap studio? What happened? Yeah, exactly. So yeah, typically they have about 20 milliseconds of delay, give or take, and that delay is enough to completely hose your control loop, and you cannot stabilize like a hover on a drone in a mocap room without doing fancier things. So even when you think it's pretty benign and like a pretty good set, like that's the best case, right? It's like super fine accuracy, but between the delays and the fact that you don't get velocities, um, you just can't do it. So you kind of always have to think about this stuff to some degree. Okay, so what we're talking about here practically, like if we start writing math out, we're talking about a situation like this. So we're assuming, there's some state vector X that we made up under the hood. And we're assuming that what we actually get are these measurements that we're going to call Y, that are a function of the state. And generally you're going to, the Y is going to be a different dimension than X, usually less than X. And this function G of X, we're going to call the measurement model. So going back to that like mocap example, it's the easy example. Like let's say it's a drone and mocap arena. The mocap system is going to give you pose, it's going to give you like position and say orientation. And the full state for that, if we model as a rigid body system, might be the pose plus the linear and angular velocity. So this G in that case is just going to pick off the position and the quaternion and like throw away the velocity information, and that's your Y, right? So that would be in that case. And there's lots of other examples of this. The idea is we can always write down this forward measurement model that takes the state and maps this into a Y. It usually throws out information though, right? It's usually Y is strictly less informative than X as a general rule, and it's noisy and stuff. So we can't usually invert this thing directly. So given a Y, I can't usually take one Y and figure out my X. And so the game here that we're going to start getting into is how you do that backwards problem, how I take some Ys and reconstruct the X, and that's called state estimation. Okay, so high level, the setting that we're in now, where we only have these Ys and they have noise on them, is now, this is like stochastic control. And so the transition we're going to make is from a deterministic setting where we assume we have X, like that's everything we've done so far, to a setting now, we've got access to these y's and they're messy and noisy. And so what we're going to do instead of reasoning over x's now, everything in stochastic control is reasoning over a probability distribution. It's the probability of x conditioned on y. So this is saying, I'm getting a bunch of these measurements. I know they're noisy, so they're drawn from some probability distribution. Often we assume it's additive Gaussian noise because that's mathematically convenient. And so then you ask the question, what's this conditional distribution on the state given all the measurements I've seen so far? And so we're going to try to compute this thing, and we're going to try to figure out how to control not just a state now, because we don't know it, but in fact, how to control this distribution in a way that's reasonable. So that's like the setting of stochastic control. So this is the probability distribution function of the state conditioned on the measurements. Okay, so how do we even start to think about that? That's a very weird thing that we've kind of like, we've gotten ourselves into this kind of seemingly pretty gnarly situation. So basically, I mentioned this like way back when we started talking about like Pontryagin and dynamic programming and stuff like this. The Pontryagin stuff does not generalize to this setting, at least not in a straightforward way. But the dynamic programming stuff, the whole Bellman thing, that does nicely generalize to this setting. And in a way that's like kind of stupidly simple and straightforward. Literally all we're going to do is now everything's probability distributions. All we're going to do, we're going to do dynamic programming, and then everything's just going to get wrapped in an expectation. So we're going to, before we minimize the cost, now we're just going to minimize the expected cost and yada, yada. So everything just becomes expectations. So let's start doing that. So like we'll say the stochastic optimal control problem is basically this. So we're going to minimize over the controls, and we have this cost function that, we're same kind of cost functions we've been writing down, right? Where it's some additive cost over the x's and the u's. And now, instead of just minimizing that cost function, we're going to minimize the expected cost, minimize it in expectation. And like I said, in principle, we can just do dynamic programming on this, and actually not that much changes. So that's cool. The problem is, as we said last time, or like a while back when we were talking about dynamic programming, this suffers from the cursive dimensionality. Like just like dynamic programming does in general, it's hard to write down this like value function-y thing over a very high dimensional space. And for basically the same reason, it's nearly impossible to write down an arbitrary probability distribution in a high dimensional space, right? Like, so how do I even do that? If you're in high dimensions and if it's Gaussian, we know what to do. We write down a mean, which is a vector, and we write down a covariance, which is a matrix. That's straightforward. But if it's some really weird, complicated distribution, like how do we even do that? Like you might think about using, so like simple ways would be Gaussian mixtures, like some of a bunch of Gaussian blobs to approximate it. Another way is particle methods, where you take a bunch of sample points and just figure out what the sample points are going to do. That's like not unreasonable. And then another way is, by like using a neural network, right? So there's all kinds of ways you can do this, but basically you have to make approximations. They generally tend to not scale well to high dimensional spaces, and life just gets pretty hard. So the game here is all about approximation schemes. Like you can't do this for real. You have to approximate. And that's basically what all of RL is. All of RL is approximate methods for solving that problem, where you plug neural nets in for all the things. So yeah, basically very hard in general, basically intractable in general. And the only things to do in general are start like figuring out how do you approximate things with function approximators and stuff like that. So what we're going to do in here, kind of in the spirit of the class, is we're going to go deep on a special case, which is the only case I'm aware of where you can actually just straight up solve this thing. And it's surprisingly useful. And so it turns out, so the thing we're going to look at is called the LQG problem. It's a special case of the general optimal control problem, stochastic optimal control problem, that we can solve in closed form. And it's basically the generalization of LQR to the stochastic setting. So it's the L, the acronym. So this is linear dynamics, basically, as in LQR, quadratic cost, and then the G stands for Gaussian noise. So what this is basically just taking the LQR problem and adding Gaussian noise to it, and then seeing what happens. And it turns out this is tractable analytically, and we get some nice results out of this. It seems like this seems simple and limiting, but kind of similar to the LQR story. Like LQR is the simple case, but it's the case we know how to solve, and it's surprisingly useful, right? You can use it in all kinds of settings. Kind of same story here. This stuff, while very straightforward and kind of the only thing that's analytically tractable, it's number one, provides a ton of insight into like kind of general things that happen in this kind of setting. And number two, it's actually extremely useful as like local approximations for nastier nonlinear problems. And like we use this stuff all the time. In particular, what we're going to see that comes out of this is the Kalman filter, which like who's heard of that? Right. So everybody's heard of that. So this is like classic stuff, but it's extremely useful stuff that you can get a lot of mileage out of, even though it's, kind of limited scope and kind of special case kind of stuff. Okay, so let's start picking this apart and looking at the different pieces. So first, we'll look at the dynamics, which, as the name suggests, are linear. So the idea here is it's really similar to LQR. Just for ease of, me not having to write tons of subscripts today, I'm going to assume it's LTI, but it works for linear time varying just as well. So it looks like this, AX plus VU like we're used to, but now we're going to also add this extra term, which we're going to call W, and this is called process noise. So we're basically assuming that the dynamics have this like deterministic part, which is like what we're used to, plus they're also driven by a noise input. And so that the idea is that every time step K, you're going to draw a W from a Gaussian distribution and add that on to the dynamics. So the dynamics are random, they're stochastic, right? And then on top of that, we talked about this whole measurement model thing and how now we don't get to see the state. We just get these partial observations. And those are going to look like this, y equals C of x. So that's a linear measurement model, which is like fairly useful actually, right? So that would be like, I don't know, I just get the pose and not the velocities, like the mocap example actually fits this reasonably well. And this we're going to assume also has noise on it. So this is going to have this VK added on, which is called measurement noise. And so this is your sensor noise. So here we've got these two different kinds of noise. One is driving the dynamics, so the dynamics are actually stochastic. And the second one is kind of modeling your sensor errors, your sensor noise. And we're going to assume in both cases that these noise terms, the W's and the V's, are drawn from a normal distribution with zero mean and some covariance that we assume we know. So WK, step K, you're going to grab a sample from this Gaussian mean, covariance big W. Has everyone seen this notation before? Most people, yeah. So this means, drawn from, and then this is normal distribution. And, Gaussian. And yeah, same thing over here for the V's. Anyone have any thoughts on why I'm assuming it's zero mean? Also, by the way, I'm going to assume everything's linear time invariant. I said that already on the A's and B's and C's. Same thing on the noise, actually. Totally fine, it doesn't change anything in the derivative. So I can have the V and the W all subscript K's on it, so the noise can be changing in time. So yeah, thoughts on why I'm assuming it's zero mean? Anyone have any seen this before? Have any ideas? So yeah, that's kind of getting at it. Because linearity, essentially, if it does have a non-zero mean, I can basically like put that in the dynamic and subtract it off. So basically, like the setup here is encompasses having a non-zero mean as well. All I would do is if I know the mean or the measurement model as an app, then I would have affine dynamics, whatever, all the same. Doesn't matter. So yeah, you can always kind of subtract the mean off in these things. It's kind of like having like a, like a delta x with some reference, x or something like that. Same kind of idea. So the zero mean assumption is not limiting. Basically, you can still handle that if you need to. Okay, so that's that stuff. And just to make sure we're on the same page, we're going to do a whole bunch of stuff with Gaussian distributions. So we're going to make sure everyone's on the same page with Gaussian distributions. So these ends and whatever, we'll talk about that real quick. So I'm assuming everyone's played with multivariate Gaussians before. Who has seen a multivariate Gaussian before and like this kind of stuff? Most people, few have not. Okay. So a little quick crash course in just the stuff we need. Normal distribution. So P of X, so the probability distribution function for a multivariate Gaussian looks like this. It's an exponential thing with a quadratic upstairs, and this is the normalization constant. So don't worry about this too much. This is just what you need out front to make this thing integrate up to 1. So n here's the dimension. This is the determinant. I'm going to call the covariance matrix S here to avoid like overloading notation with the P for the cost to go function later. And what this looks like is e to the minus 1/2. And then the thing in here is x minus the mean, and then the inverse covariance, and then x minus the mean. Cool. So most people have seen this before, right? So that's that. The mean here, the mean of the distribution is that mu in the definition over there. And we're often going to call this x hat. And this is also the expectation of x. People have hopefully seen it. People have seen expectations before? Quick show of hands. Just about everybody. Excellent. And this thing is a vector in Rn in general, right? So we're assuming this thing is a distribution in n dimensions. So everything's vectors. X is a vector in Rn, mu is a vector in Rn, and then that covariance matrix S is an n by n matrix, right? So the covariance is S, and the definition of this guy is the expectation of x minus mu times x minus mu transpose. So you think about that for a sec, what this is, I'm going to take all the x's, I'm going to subtract off the mean. I'm centering this thing at the mean. And then what this is really trying to measure is the spread of the distribution. Basically, the multi-dimensional variation of like generalization of like the standard deviation or whatever, the variance. And in particular, this thing, this is an algebra. So this is a matrix. And what this is trying to do is just capture the variance in all directions. That's kind of the idea. And we say that this thing, so this is a symmetric matrix because this is, and it's also has to be, in general, this is got to be positive semi-definite, but we're going to generally assume that it's strictly positive definite. The only reason can anyone tell me when it's going to be semi-definite, not strictly positive definite? What does that correspond to? Well, no. So this is in like n dimensions. If it's semi-definite, it means it has a zero eigenvalue. Well, it means that specifically the Gaussian is smushed in one dimension. So if I had like, if I'm in 3D and I have a distribution that's confined to a plane somehow and doesn't have any probability mass in like one direction, that's when this happens. So in general, if we're like, normally if we are in n dimensions and we have noise and stuff, we're gonna generally assume this thing is strictly positive definite, which means there's just probability mass in all directions. I don't know what that corresponds to. Okay, so that's that. And just to review the definition of an expectation. So if I have some function f of x and I want to take its expectation, what this really means is we're taking an integral of f weighted by the probability distribution. And this integral we're assuming is like over all space. Right? Cool. And the last little nugget that we need to kind of do what we're going to do today is we have to know the definition of uncorrelated. This is going to show up. You ever heard of this before? What does it mean for two random variables be uncorrelated? Kinda, not exactly, actually. It doesn't exactly mean they're independent. Yeah. Cross covariance is 0. Yeah, so if I have two, like let's say x is 2D vector and I have x1 and x2, two variables. If x1 and x2 are uncorrelated, that means that the off diagonal term in the covariance matrix is 0. The like 1, 2 or 2, 1 term that corresponds to that cross term that corresponds to those guys is uncorrelated. Right? Does that make sense, everybody? It's like they're in many cases, yes, but the definitions are actually different. You can have one and not the other. It's a little subtle. You can Wikipedia that one, or come bug me after. So they're subtly different. If you're being like pedantic about it. Okay, so this is like if I had x and y, right? It means the following thing. So like that cross term, right, is going to be 0. Okay. Okay, so any questions about any of this? This is like my very, very brief crash course in like multivariate statistics. This is all we need for this. So if you've seen this step before, we're good to go. Yeah. Oh yeah, sorry. That was dumb. Okay, thank you. Excellent. All right. Trucking along. Okay, so now we know some statistics. So now what we're going to do is start looking at this whole dynamic programming thing in this stochastic context for this LQG problem. So we're going to start by just like writing down the cost function that we're talking about. So what this J actually is, and so we're going to, again, wrap everything in expectations. And this is going to be our standard LQR type of cost function. So I'll write the terminal cost first, and then it's the usual sum over time steps. And I guess maybe for convenience, I'll put the 1/2 out front. And then it's X transpose. The usual LQR thing. And now we're going to start doing the dynamic programming thing. And this is where there's actually some like very deep results in here that are really kind of interesting, like things that are often glossed over, I feel like, that are subtle and actually really, really deep. So hang on. We'll get you some good stuff today. So we start at the end like usual, and it looks very much like the LQR thing. We're just wrapping things in expectations. So we got the terminal cost at time step n, just like before. It's just got this expectation around it now. And just like we're used to from LQR, we're going to assume that the cost to go is quadratic and stays quadratic because linearity, blah, blah, blah. And we're going to call the cost to go Hessian P. And we're going to start with Pn equals Qn, just like before, right? All that stuff carries over. So now what we're going to do is the backup. We're going to go to Vn minus 1. And just like we did before, it's min over U. And now it's almost the same, but we're going to pick up some new terms. So let's write this out. So it's the one-step cost. This is the same as before. We've got the U term. But now, so then so we have one-step cost, and then we've got the dynamics plugged into the cost to go, right? So it's the cost to go for time step n with like the state and controls from this time step plugged in the dynamics. And that's almost the same as before, with the one exception that we've now got this additional noise term in the dynamics. So that looks like this. I guess this should have been n minus 1. So yeah, now we have the W. Pn. So again, exactly the same as LQR with the one exception that now we have this W in here. Okay, so now here's a question. What is this expectation over? What's the only random variable in this problem so far? The noise. So the expectation here is over the W. That's the only random variable. That's the noise, right? Cool. So keep that in mind. And I should go. Yeah. No, I guess they're not really legible. Just for. Okay, cool. So keep that in mind. And now what I'm going to do is I'm going to like kind of expand this out, like FOIL this or whatever, and we're going to split this into a couple of sets of terms. So this is mean over U, expectation. And so what I'm going to do is I'm going to group stuff together. So we've got this set of things. Let's see, then we got A plus BU, E, and then A, U. Okay, so this, and expectations linear, so I can split it up, right, and write it into expectations. And then I have this second set of terms. So that look like the following. Plus okay. So so this is just this with stuff like spread around, right, a little bit. The key takeaway is the first just the standard LQR stuff, right? Let's write that down. And then the second line. Okay. And now we're gonna play some games. So remember we talked about what it means to be uncorrelated? Okay. So let's think about this for a second. -1. That's where I am right now. You control the time at -1 is like what I'm doing, right? And then this is the noise that I'm drawing from some Gaussian with covariance W, whatever, at time n-1. That's going to like propagate me to the next time step, right? So I'm already here. These things, I have to figure that out. Then I'm going to like take a random draw. So the question is W correlated? And yeah, head shaking is correct. Basically, the way to think about this is like, I'm here, I am where I am. That W gets drawn from some distribution right now. I'm already here. It affects so say another way, Wn-1 is correlated with Xn, because that's part of how I got to time n, but I'm drawing it now and I'm already here. So it has no correlation with Xn-1. Is that clear to everybody? Okay, so these are uncorrelated, which means this cross covariance. So the definition of uncorrelated is cross covariance 0. So both these terms, because these things are uncorrelated, drop out and is 0. This guy's 0, and this guy's 0. So let's write this out. Noise sample drawn at time k is like, basically, if I were saying this in plain English, I would say like has nothing to do with the state or control, because I'm deciding on what the control is based on the current state, right? In my feedback controller. Like I basically have to pick that U before I know that what that W is at time k. Um, so that xk, it does depend on past noise. It depends on wk minus 1 and all past w's. But not on wk or future w's. So all this means that these things are uncorrelated. And so those terms are 0. What's that? The thing here that's happening is more, it's not that, it's this like arrow of time idea that like basically that W is being drawn like now or in the next time over the next time step and has nothing to do with like the current X. It's the idea that like the current state doesn't depend on noise drawn in the future, like they are uncorrelated. That makes sense. It does depend on previous noise, but not future noise. Yeah. No, you can't in general. I mean, in this case, it's 0 anyway, but like basically what you're kind of arguing is that because this guy, which we're about to talk about. Sure, sure, but is this term 0? Right. Why? Because it's basically W squared, which is a covariance, right? So W has 0 mean, but W squared. Similar argument here. This works. So yeah, I mean, like it's not something subtle. Literally, the definition of uncorrelated means that it's like if W and X were cross or in fact W and X, this would uncorrelated. That's the thing that's happening there. It's not really a 0 mean argument. That's, I mean, it is not. Like, this would still hold up if government. But this does not depend on the term. Yeah. Yes. Yeah. That is right. It is 0 in expectation. Expectation around the whole thing. Yeah. Anybody else? Yeah. Foil. I just multiplied this thing out. Like literally. So the terms that had the cross terms involving W. The first row is just regular LQR, and the second row is all the stuff involving noise. And the key thing to note, yeah. You could like, so this basically, if we, okay, so I guess you could write that down. The upshot is you don't have to, at least not in this context. In this LQG context, because linearity, changing the sample rate on the noise just basically means you're letting the noise integrate for longer, aka average out for longer or whatever. And so basically what you would do is just scale the W, the covariance to that just gets scaled by some amount proportional to sampling. So you can kind of pick your sample rate here and it doesn't change anything. It just changes like the covariance on the W. Yeah. Yeah, so the standard deviation scales like square root of t. The covariance scales like t, right? Like common sense, right? Like square root. The, this is sigma squared, right? So it's t and not square root t. Yeah, yeah, cool. But yeah, that's exactly the right thing. Okay, cool. Anybody else? This stuff's a little, yeah, this is a little bit of tricky. And there's some weird stuff. So basically we argued those terms go away. And then what about this last term? Almost, right? It's like capital W with this T thing. So it's basically like proportional to capital W. It's basically like capital W times P. So trace. I mean, literally it's trace of N times W, which maybe isn't obvious, but I'll show you how that works out in a sec. So yes, almost right. This is basically this thing, some like variance thing. So yeah, it's proportional to W. And the big thing is this is a constant. It only depends on big W, right? Only depends on the noise. Doesn't depend on the state or anything else. So, right. Okay, so I mean that was like a little bunch of math tricks, but there's something very deep that came from this, that I will now explicitly spell out to you. Um, so what this told us is that the noise terms in this whole thing, um, all the stuff that coupled dropped out. The only thing left is this constant term that just depends on the noise covariance cost over plain LQR stuff. So if you think about this for a second, the repercussion here is that the noise terms, all the stochastic stuff, has literally no impact on the controller design or the feedback policy that you should use. All it does is add a higher cost. Literally what this says, if I just do vanilla LQR on whatever my expected X is, that is optimal. And basically all that's going to happen is I'll get whatever I would have gotten in the deterministic case, plus this. And I can't do anything about it. That's the best you can do, which is kind of interesting. Yeah. 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 There's some sense in which this is like kind of this argument about like Gaussian being the maximum variance distribution, blah, blah, blah. It's like the most unpredictable it could be, and you can't really do anything about it. And in the zero mean case, like this is all that happens. Like basically you just like throw up your hands and do LQR, and that's provably the best thing you can do, which is then it's not zero mean Gaussian, right? Then it would be something else. It'd be like the word for the standard term for that is colored noise. It's noise that where there's some time correlation, like there's some underlying dynamics going on. And what should happen in this context, what you should do in that case is try to put that in the dynamics. So if you say there was some kind of trend in there that wasn't just pure randomness, you should try to figure out what that is and model it in the dynamics model and estimate it out. And then if once you subtract that out, what's left should be Gaussian noise, right? So that's the context in which that idea is very pervasive, like, and it's kind of really deeply tied up in how we smush control problems into this LQG setting. Kind of the idea is you should model everything you can. If there's something that's not zero mean Gaussian in there, Could be as simple as it's biased up with some mean. Could be complicated where there's some time varying like bias dynamics going on in there. You should do your best possible job trying to model that out. And after you subtract off all that stuff and put it in the dynamics, what's left should basically be white noise. And if you can get to that point, then this is the answer. But to get to that point, you often have to do a good job of like trying to eke out every last little thing that you can. That's kind of deterministic in there, right? Okay, cool. So let's see. Let's write that down. Noise terms have no impact on the controller design, which is kind of crazy. You just get a higher cost. Okay. So this has a name. This is like a deep result actually in like theory of optimal control. This there's kind of like two big picture ideas that I'm now gonna like, kind of spit out random names for. Okay, so the first one is called the certainty equivalence principle. And what this says is in this LQG setting, the optimal LQG controller is just the deterministic LQR controller with X replaced by expectation of X. So basically, throw expectation on it, and like it doesn't change the control design at all. Use the same control policy, and you're just throwing the expected X in there, your best, estimate of X instead of the actual X, and that's the optimal thing to do. That's like the best you can do. That's kind of what we just figured out. And then this like closely related other term that you're going to hear is called the separation principle. Has anyone heard of either of these things before? Certainty equivalence or yeah, where did you hear these things? I guess like which one? Okay. Well, you just read ahead, cheated. Good for you though. Cool. Yeah, so okay, then the separation principle thing is these are closely related ideas. Basically what this says is for LQG, we can basically the idea here is like if I do LQR and plug in expectation of X, that's it. And so what this tells you is you can design the controller basically assuming it's a deterministic problem. And then you have to also design an estimator to get that expectation of X, right? A state estimator, in other words. But the idea here is that you can separate those two design problems and they don't have to interact at all. Like you can design whatever kind of statistical estimator you want to get expectation of X, and you can design this deterministic optimal controller, and you just hook them together and you're good to go. We can design an optimal feedback controller and an optimal estimator separately, and then hook them together. Yeah. You're never adding noise in the controller, at least not in our world. You might do this if you're in, RL and you believe that the world is stochastic, but usually we don't want to do like add noise to our controls. So yeah, we're never doing that. What this is saying is that like I can't know the noise, right? Like I'm sampling it from RAM. At each time step, there's some noise, and like it is what the universe sort of did to me, and I can't really control it, and like I have to live with it. But what this is saying is that like, at least in this LQG context, make under these assumptions, right? The best I can do is to just use the deterministic controller, the LQR controller, assuming there's no noise. I just plug and then like somehow, you said Kalman filters, I'll say it, but like we didn't get there yet. But yeah, some statistical estimator, Kalman filter say, or whatever, to get that expectation of X. You do something to get that estimate of X, whatever estimator you want to use, and you plug it into the deterministic LQR controller, and that's the best you can do. Well, so literally it's a constant. That's what we showed, right? So it doesn't do anything. It drops. So like, remember, like when I solve for the controller here, what did I? So it literally has no impact at all. So I can leave it in there, but as soon as I matrix in the Riccati thing, as soon as you do that, the constant term drops out and does nothing, right? So it doesn't affect the control policy at all. It does nothing to you, but it's still in the cost. So literally all it's doing is pushing the cost up by some constant amount that depends on the noise variance. But you can't do anything about that. It doesn't affect the controller, and you just kind of stuck with it. That makes sense? Cool. Anybody else have any? Yeah. Oh yeah. Basically all the time. So so this is cool. This is actually a very deep result, right? But the punchline here is these two things, the certain equivalence thing and the separation principle thing, they only hold in the LQG case. They depend critically on one, the distribution being Gaussian, and two, the dynamics being linear. That's kind of, they depend on both of those things. And so if you violate either of those assumptions, so if you have nonlinear dynamics and or you have non-Gaussian noise, like multimodal noise or whatever, all bets are off and you can't do this. But then the problem becomes intractably hard, and we're kind of screwed. So this is why we often make these assumptions, like in practice anyway. So yeah, let's write that part down. Uh, Basically I rain on everyone's parade and tell you life is hard. Yeah. Yeah, 100%. We do it all the time. So basically what I'm telling you is here, this falls out of this set of assumptions we made. This is actually very cool and means that you can kind of pretend you're living in a deterministic world when you design your controller and then just design some kind of state estimator and hook them together, and that mostly works. That works because of these things. This is never totally 100% true in real life, but like for the same reasons we get away with using LQR on nonlinear systems all the time and all that kind of stuff that we've already shown you, like convex MPC works surprisingly well on nonlinear systems. Same argument, like as long as your distribution is really what comes down to, so linear-ish, close enough, local tracking, blah, blah, blah. The big one though is actually not so much Gaussian, but unimodal on the statistics. So if your distribution is unimodal, then you can generally get away with this. If your distribution becomes multimodal, what that's really kind of saying is you don't really know where you are. You might be here or here. And what ends up happening here that's subtle in that kind of situation, which is not uncommon in hard problems, really what it's saying is you don't exactly know where you are, and you need to do something with your controls to figure out where you are, if that makes any sense. So like I can give some examples there, but like basically like if it means that your control decisions are coupled to your measurements in such a way that you can't know where you are without putting in particular control inputs. So like a good classic example of this that I got as a grad student in like a stochastic control class was like, assume you've got like your, I don't know, your double integrator problem or whatever, the sliding brick, or even just like a thing where you have velocity inputs. So it's like linear system and it's on the line. But your measurements, you only get to measure the absolute value of the position. So the gist is now you don't know if you're on the left or the right of the origin. So how do you figure that out? So I have a control input, I have the force input, I can push it left or right. So the idea is if I have no noise on the measurements, then it's pretty easy to figure out. I basically give it an input, and if I'm on the left and I push left, then the absolute value goes up. If I'm on the right and I push left, absolute value goes down. So I can use this kind of like by choosing my controls, this is a simple example of showing you like how the controls are coupled into the measurements in a way that you have to know what your previous control was and the next measurement to kind of tease out what side of the origin are you on, right? But then once you know it, you're good, right? So there's lots of examples like this where you have to actually sort of like choose your controls to tease out where you are. And so this kind of gets at this idea of like kind of either multimodal distributions or like kind of nonlinear coupling, right, between the measurements and the controls. So that, you know, like the controller, another way of saying it is the controller fundamentally in that setting has to reason about the distribution and not just the mean. That makes sense. Yeah, cool. Yeah, okay. That's a fun problem, by the way. Like basically you can write out, it's nice, it's low dimensional. You can actually write out like the full stochastic problem in that setting. Like you can actually either using a particle method, just like tons of samples, or you can actually just like bin the space. You get a bimodal distribution, right? Like if I know nothing and I tell you, you know, my measurement's 1, could be at +1 or -1 with equal probability, right? So you have this bimodal distribution, and then what do you do? And so the noisy measurement case of that's also interesting because if you put in a little control input, you know, that's smaller than the noise, then you don't really know. And so you can build confidence and you'll start getting like the modes will shift around a bit, right? So that's a cool, I mean, maybe we should do this, but yeah, it gets gnarly. Like that set of ideas of like, the reason I didn't like make you guys do something like that is because the set of ideas that you can use to solve that, you just like write down the probability distributions, does not scale past like the, you know, couple dimensional case and are not very useful in practice, but they're fun little things to play around with. All right, so sorry, I got slightly sidetracked. So neither of these results holds in general. But they're super, super common in practice. To design, I guess, you know, like suboptimal policies. Right. So generally speaking, as long as you, and honestly, the practical engineer answer in most situations, if you have multimodal statistics where you don't really know where you are, the answer to that is probably to add more sensors until your statistics are unimodal and you can make this assumption. And right. So that's the practical answer. There are situations though where you do truly end up with multimodal statistics and hard problems like this. Like one that I've seen that's cool is like there's like a bunch of, you know, kind of like terrain relative localization problems, like underwater and stuff like this, where you use sonar data and try to match up where you are from like a map of the terrain features, where you have multiple hypotheses and it takes a while to figure out where you are. And part of that is, oh, I think I might be here or here. Well, let me look over here. If I steer this way, you know, you can do hypothesis testing. You can say like, well, it could be in these 3 different places, and you know, the terrain to the left, if I were in this place or this place, would look different. So based on your control move, you can use the control moves to help you figure out where you are, right? So that's where this certainty equivalence doesn't work and where it gets important. All right, cool. Let's see how much time we got left. We got like 5 minutes left. Should we do one more thing? Should we do one more thing, or should we? Yeah, nods. Yes, cool. Let's do one more thing. One more thing. Why not? We got some time. All right, cool. So let's see. So the next step here, which we'll really get into next time, is optimal state estimation. So we right here we basically said, you know, for this LQG problem, the control problem's the same. I don't have to change anything. I just do LQR. But what we got to do now is worry about this expectation. So now we need a state estimator and an optimal state estimator because we want to be optimal. So a quick sort of foray into that, which we will really dig into next time. So the question is, what should I optimize? So I've got like some probability distribution. So what I'm ultimately trying to do here is I have some measurements. They're random, they're noisy, whatever. They're drawn from some distribution. I want to somehow take those measurements and, you know, my measurement model, my dynamics model, and I want to figure out like where I think I am, right? Like, and, you know, based on this stuff. what should I be optimizing? So to kind of play with this idea some more, let me draw you a weird probability distribution. So we'll be in 1D or say, this is X, this is P of X. I'm just going to draw some weird thing. Ah, damn it. And I'm going to ask you, what would be a reasonable choice of, thing to optimize here? What should I optimize? That's a very reasonable choice. So that would put us here, right? Probably. So that's called the map estimate for maximum a posteriori. That's often not what we do, though. And like least squares, for instance, what do I do in least squares? In least squares, I'm trying to minimize the sum of the squares of the errors. So that's called a minimum mean squared error estimator. What would that get me here? It's basically trying to like the where like the areas will balance. I'm going to put somewhere relatively low probability area, right? Which is probably a bad place to think I am, right? So this is probably somewhere over here. Okay, so let's write down what these are. And you could think of other things. These are just maybe a couple of the most common things you might think to do. This is argmax of say P of X given Y. So remember, we're trying to figure out where we are. We have this distribution based on like the measurements, right? So we take this thing and we're trying to say, okay, the most likely place I am is probably the peak of the distribution. Cool, very reasonable. Right. And then the other thing we could do, which is also very reasonable, is basically least squares, which is this kind of idea of minimum mean squared error. And so what this guy is doing is trying to minimize the expectation of x minus x hat transpose x minus x hat squared error, right? This is squared. Okay, so what happens in the case of a Gaussian? Yeah, in a Gaussian, these things end up coinciding, which is kind of cool and kind of why you probably never bothered to think about this before. Because in the Gaussian case, it doesn't matter. Like I think, yeah, I'm gonna save. We're like basically at times. I'm gonna save some more nuggets for next time. Let's see. I'll probably revisit this next time. Okay, cool.